morning and welcome to the Grasland Thursdays. Grasland Thursdays is a series of webinars we organize every Thursday at 10 on various HPC topics, such as this one today on computing precision, which will be presented by Hadrien and Vincent Lafage from IJCLab. But first, let me give you a little presentation of the organization team. It's Pierre Aubert, a research engineer from the lab, a French laboratory of physics and particles in Annecy, in the French mountains, and Karim Azoum and I from TerraTech, within the French NCC called CCFR, and with the lab of Annecy, we co-organize the Grasland Thursdays and the Grasland School. Because those 17 Grasland Thursdays you will discover are held by 9 incredible teachers who will each one of them give you webinars on their topics, introducing at the same time the program of the summer school. So, what is Grasland School? It's a free summer school dedicated on programming and optimization on heterogeneous architecture. It was created 2 years ago by Pierre Aubert with a few people in Annecy, and we, the French NCC, joined him last year to help him develop it not only in Annecy, but also in 12 satellite sites among 4 countries. Those satellite sites helped us reach more people by broadcasting the school live in their locations. The summer school had a 2-week program, 1 week on CPU, 1 week on GPU, but everybody was free to choose their courses they wanted to attend thanks to our a la carte option. And we finally trained over 500 people, and everything is available still on replays on our website and our YouTube channel. And we'll give you the links later on the chat. So you can access it if you want, but obviously everything is in French. But like this year, we are going European, and so all will be in English, like this webinar. So you have various ways to attend the school. As you'll see in the video, I'm going to launch for you later. And also we invite you to be part of the team and become a satellite site yourself if you want to host the school at your place. We are able to provide you everything, all courses, containers, access to the teachers, and also to connect you with our growing HPC community. So now, let me play the video for you.
Do you sometimes feel limited by your resources or unsure how to maximize the potential of your HPC resources? Imagine a place where collaboration, creativity, and learning converge with high-performance computing. Welcome to Grasland School 2025, Europe's leading summer school for HPC. Taking place from June 23rd to July 4th. Over 2 weeks, students, academics, and industry professionals from across Europe will explore the frontiers of programming while building a vibrant community. Together, we'll discuss programming and optimization on heterogeneous architectures, highlighting their respective characteristics and limitations. You'll have a unique opportunity to explore generic optimization methods, as well as the latest technologies and languages for achieving optimal performance. The school is free and open to everyone, and you can participate in person in Annecy, France, with the teachers, at one of our satellite sites in Europe, or online via our live streaming. You can choose from an intensive program or a la carte courses to develop your skills at your own pace. With the first week dedicated on CPU and the second on GPU architectures, you will study computational accuracy, vectorization, parallelization, compilation, memory profiling, unit testing, and the various programming languages C++, Fortran, Rust, Python, and Julia. In addition, we will study the MPI, OpenSHMEM, OpenMP, TBB, EVE, Kiwaku, Cycle, Thirst, CUDA, OpenACC, Vulkan, NumPy, Number, CuPy, CUNumeric, JAX libraries, and Legit, as well as computation with PyTorch and TensorFlow, and the G++, Clang++, NVC++, NV Fortran, G Fortran and DPC++ compilers. Throughout the course, you'll discover and use profiling tools such as Valgrind, Perf, Macau, Nsight, Malt and NumaProf. Each session leads to a practical challenge, the simulation of Gray-Scott's diffusion reaction, which tries to describe how a chemical reaction evolves over time. Simple to understand, but complex enough to push the limits of optimization. Thanks to our specially designed Docker containers, you'll have access to a complete working environment to follow courses and exercises on your laptop or supercalculator. Throughout the program, you'll be guided by a dozen expert instructors, leaders in the field of programming and HPC. You'll have the opportunity to ask questions and chat with them live on Discord, so you can tailor your learning to your needs. Join our growing community of over 500 users to find answers, exchange ideas, take on challenges together and build bonds that will last well beyond the program. You can also join the Gray-Scott School European network of satellite sites, not only to attend the courses, but why not become a satellite site yourself and host the school in your location? You just need to provide a room, a contact person, and access to computing resources. We'll provide courses, tools, and Docker containers for a seamless learning experience. Gray-Scott School is free and open to all. It's your chance to master advanced programming and optimization, engage with a growing European HPC network, and push the boundaries of technology and training. You can kickstart your journey now by joining Gray-Scott Thursdays, a free webinar series previewing the school's courses. Don't miss out. Register today to attend, whether in person in Annecy, France, or at one of our satellite sites in Europe, or online via our live streaming. Gray-Scott School 2025, where HPC meets your potential.
So thank you for watching our video. If you have any question regarding the school, you can ask them in the Q&A section, and Pianai and Karim will be glad to answer you. So thank you for listening to me. Now it's time to give the floor to Hadrien and Vincent. Have a good webinar.
Good morning. I'm Vincent Lafage, an engineer in IJCLab, and we'll address today's issue of floating point accuracy. Our Gray-Scott School is dedicated to high-performance computing, but we would rather not compute false things fast. We would prefer to keep at least some accuracy, and so we have to delve into the subtleties of floating point. So, welcome to this tour of the floating world. This is the name that Japanese use for their woodblock prints. This is about the most poetic slide of the whole talk. We would soon be into the gory details. So we'll address what every computer scientist should know about floating point arithmetics, and maybe a bit more, starting with a description of numbers, the one we believe we know, the real, the algebraic, the constructible numbers, the one we are deeply brain-wired with, the decimal number, and the one that looks familiar but are not quite, which are the binary number, and their earthly restriction, the floating point numbers. So we don't see them as very difficult, as in fact we are exposed to them as primitive types. We have seen in Computing 101 float doubles. Some of you know about long doubles and maybe quadruple precision. Nowadays, GPU vendors also want us to believe that half precision is enough. we'll see what turns out. So when computation doesn't turn out as expected, we'll try to understand why and how. It goes through rounding errors, conversion errors, how error propagates, and how error are composed. As an heuristic for accuracy, we'll see that sometimes an approximate formula gives a more accurate numerical result than the exact formula. And today I will conclude on the non-dimensionalization on formula entropy reduction. The other point will maybe have more time to be developed during the school, but you can take a look at them in the slide that will be on the site. At this point, I will turn the mic to Hadrien for addressing subnormals or so-called denormals floating point number on the many issues they provide us. So floating point bugs are quite subtle usually, but the consequences of those bugs can cost and kill. Among the famous examples, Patriot missiles used to fight Scud missiles during the Gulf War in 1991 were programmed with a time counter in float. This is a bad idea. It led to a 600 meters of error for intercepting the Scud and led to 28 killed in action as well as 100 injured. Even 1 decade before, in the Vancouver Stock Exchange, the error accumulated over 2 years on the value of a stock market index stored in binary in a float led to 52% of error. So the valuation of the stock was $524 instead of $1,000. So using float for financial computation is also a bad idea. So how comes that the computer leads us to believing such false results? So the initial paper I was referring to, what every computer scientist should know about floating point arithmetic, dates back to 1991. So this is a milestone in the community. Of course, you already had a very interesting paper dedicated to floating numerical analysis. There were high-end paper. So this one is more accessible and give you a tour, but it's quite mathematical oriented. And so you can also look at on archive to my paper condensing some of the result of this one. So the leading title in the abstract is floating point arithmetic is considered an esoteric subject by many people. We'll see that it's indeed the case. Let's start with format. The one that is dominating the world of computation, saying that computing is about representation. We can represent floating point number in a computer using something like scientific notation, where you have a significand times a base at the power of an exponent, where your significand is an integer number, and the exponent is also an integer number. And computers are quite good at representing integer. So, in fact, we'll not use an integer significand, but a normalized one, which we will call a mantissa. And as we are in base 2, the most significant digit is always 1. So, as a trick, the hardware vendor will usually encode this leading one in the silicon, and we'll save 1 bit in the representation. So for floats, you have 23 bits of mantissa, and those that don't include the leading one. So we have 24 effective bits of mantissa. For double, it's 53 bits. And for long doubles, in this case, it's not 64, but only 63. Okay, so we have a sign, we have a mantissa, the base is 2, and we have some exponent. And the last newcomer is the half float, where you have only 16 bits in totals, including a mantissa of 10 encoded bits, which means 11. So your resolution is 1 in 2048. In the FPU registers, we widen the mantissa with 3 extra bits, the guard bit, the round bit, and the sticky bit. All these extra bits allows to have better accuracy in the intermediate result so that we can round the result more accurately. We'll see this soon. I started with the nowadays formats, but you have to imagine that before there existed a huge number of them. Each vendor had one or many formats depending on the machine. So I show you here only a limited, very limited amount of those old formats. You can go to the URL to check. There are 3 times as many as these ones. It was quite frankly a mess. You were far from getting reproducibility. Hopefully, Professor William Kahn came. He's dubbed the father of floating point. He was a consultant for the Intel FPU x87 that is buried deep inside all our processors, Intel and AMD, and got the Turing Award in 1989 for his fundamental contribution to numerical analysis. So I really encourage you to go to the URL at the bottom of the slide. It's very rich with paper, with inspiring papers. So let's go deep into the detail. And we have seen, we have one sign, we have some exponent, which is in fact shifted around 127 on the fraction part of the mantissa, 1 plus m. So the first number that you see on top here on the first line is the encoding for 1. 2 to the power 0 times 1 plus 0. All the following numbers, 2, 3, show you that in fact you will always have some exact representation for integers up to 2 to the 24, from minus 2 to the 24 to plus 2 to the 24. But when we want to address really decimal number, some of them can also get a representation, an exact representation, like 3.5 or 3.75. Of course, negative number have only the sign to change, so they can also have exact representation. 1/2 get an exact representation, but things go wrong when we address the standard, the seemingly unsuspecting 0.2. This does not get a finite representation in base 2 because it's 1/5, and 5 is not congruent to, is prime respecting to the base of 2. Okay, 1/3, of course, it doesn't work in base 10, but it doesn't work in base 2 as well. Square root of 2 is irrational on pi as well. So a quick overview of the spatial representation. 0 shouldn't be representable in the standard as we always would have 1 plus something to some power. So there is a spatial representation with all zeros. And his little brother 0 minus, which is the opposite of 0, and it requires also a special representation. It can be useful for complex number computation. Then we go all the way to the largest float that you can represent. In simple precision, it's something around 10 to the 38. And if you go to the next, you increment your binary number with 1, you get the special representation for plus infinity. This is some way to encode what would otherwise be an overflow. You can also have meaningless computation, such as 0 over 0, and you will encode the result with an exception or not a number. So you have to decide. Even your not a number are of two types. You have the quiet one that gets propagated from step to the next step in your computation, and signaling not a number. On this signaling not a number, they in fact just stop your program, and this can be useful when debugging. In the same way you have some largest float, you also have the smallest positive float, but the smallest positive float at 1 to the 10 to the 38 is not in fact the smallest representable float, because there is a smallest denormal float, which is 6 order of magnitude below. The largest positive denormal float is just below the smallest positive float, but Hadrien will address them in more detail. So if you want to convert your favorite number, you have the link at the bottom of the slide. You can see this hexadecimal representation for all your number in C, as is described in this slide with the %A format indication. And in the same way, you can do it in C++ with xfloat. You can do it in Fortran in a rather roots way, rather crude way. You have to interpret it. In Python as well, and then small hint, when you speak of float in Python, it means double precision. So you have to use NumPy float 32 if you really want float single precision. You can do it in Ada language as well as in Rust. You have to define some function to extract the component, but it's doable, and I encourage you to use this to pass the exact value of your floating point number to Collit. In fact, we have seen in quite a few slides that what we believe are primitive types are in fact objects. These are objects with components, the sign, the mantissa, the exponent, and you can use accessor to this component with copy sign or fraction on exponent, frexp, or depending on the language, fraction on exponent can be accessed with a separate accessor or with the same one in C, C++, Python. IE arithmetic provided a way to standardize this with log B, scale B. This is what we call a leaky abstraction. So usually floating point number are the best used object. Most people don't use this accessor, which is a very good object-oriented practice. Accessor should be limited to the designer of the library, in our case, the math library. We call it a leaky abstraction because this object, the float or the double or any resolution, lets us see through with primitive operation plus multiply minus, let us access to data such as epsilon, the radix, the precision. So in fact, we would not even need this accessor to do most of the job we want. So this abstraction is not leak-proof, but most people use it right. So we will start with some very basic initiation. You have likely seen people wondering why on some computer 0.1 plus 0.2 is not 0.3. So we'll formalize this with, we'll name sigma the sum of the two first numbers, and we'll compare it to C using delta as the difference of sigma on the expected result, with A is 0.1, B is 0.2, and C is 0.3. And here you can see that provided you display the number, the floating point number with enough resolution, you find some extra digit deep inside the representation that is quite unexpected. But the wrong representation of 0.3 is for FP32 quite equal to the sum of the false representation. So delta is 0. These results are surprising by themselves, but at least the equality is kept. And when we go to FP64, we would expect the resolution to get better. But in this case, we see there is some small discrepancy of 10 to the minus 17, which is quite frankly a bad thing. It's small, but it's really not equal. Then you go to long doubles. Everything is still surprising, but the identity is kept. And in FP16, okay, it's wrong all the way down, so I will not comment on this. So in fact, this comes from the fact that all binary are decimal, but some decimal are not binary. Well, in fact, a large number of decimal are not binary. So it means that when you convert your decimal number in your computing language to binary, some rounding is needed, as it will not get into an exact representation. And you can see it for 1/5, which is 0.2, which has, in fact, an infinite expansion. And the discrepancy is about, in float, in FP32, 2.3 billions of error. So it reminds us of what Kronecker, the mathematician, said: God created the integers, and all else is the work of man. So when we try to see the mathematical properties of decimal and binaries, in fact, their mathematical definition is very similar, and they have a lot of good properties in common. So a decimal is some integer divided by a power of 10, while a binary is some integer divided by a power of 2. So B is a part of D, but D is not a part of B. So 1 is in D, but it is not in B, as we have just seen. Already some consequences is we should not use floating point number for financial computation. For binary, as for decimal, we have the closure of the operation, and the sum of two binaries is a binary, the product of two binaries is a binary. We have commutativity. X times y is y times x, and the sum as well. We have associativity of the binary sum and binary multiplication. We have distributivity. We have the good properties of the order relation, transitivity, antisymmetry, reflexivity, as well as the fact that it's a total order for each of your binary number. You can compare them, and one or the other is bigger than the other one. Okay, on the topology side of things, even if B is a very small subpart of Q, the rationals, the binaries are dense in R. So in principle, we could arbitrarily get close approximation to the real number, to any real number. But we are not using binary. We are using floating points, which are finite binary numbers. Okay, except the one that use floating decimal, but we'll only have one example today. It's not very useful in everyday life. We lose closure. The sum of some decimal cannot fall exactly, the sum of two floats cannot fall exactly on one float. So we need to round these and provide for extension. When the sum or the product goes overboard, we have to represent the result as this overflow as infinity, which is not exact infinity for the mathematician. If we multiply 0 times infinity, we have not a number, because 0 is in fact something that represents underflow. And in fact, most of the number are the result of some inexact operation. So when you sum two numbers and you have to round, when you multiply two numbers and you have to round, most of the time your CPU, your processing unit, will return inexact. This is a flag that means, okay, I had computed some result, but I had to round this more exact result to the limited format. So the result of this operation is inexact. You have to ignore the inexact flag, because you would get most of your computation are inexact. Okay, we keep the commutativity, which is a very good thing, because most of the time the formula translators of the world will change the order of operations. But we lose the associativity, which is a pity, because optimization means reordering, and reordering change the order of evaluation. So we know that we don't compute what we have, most of the time, what we have asked the computer to compute, because of this associativity. And it gets wrong when you vectorize, it gets wrong when you multithread, it gets wrong when you GPUify. In the same way, we lose distributivity, and we keep most of the ordering property except the total order, because of not a number that is not, you cannot classify. On the topology side of things, B can be dense in R, but the floating point number being only a finite part of B, or if you want of D, they are dense nowhere. So we lose all properties, all interesting properties. So to demystify rounding, we have closest representable neighbor for most number in R. So when we compute with real number, we have to look around this number. We have x minus and x plus, which are floating point number, and they are on both sides of this small x real number. So the discrepancy, the interval described by x minus to x plus, is wide by what we call 1 unit in the last place, 1 ULP. And we can imagine some real number m, which is the median of x plus and x minus. And this number m defines where your x will be rounded. The correct rounding, in the case that is shown on the slide, will round the real x to x plus, which is closer, because x is between m, the median, and x plus. It means that to provide the correct rounding, the best possible rounding, we need at least 2 extra bits beyond target accuracy. So this is what we saw as guard bit, round bit, and sticky bit. So in this case, 3 extra bits. But we can need even more, as we will see soon. So the takeaway of this slide is we have 3 ways of rounding. The correct rounding is when you always compute with at least these 2 extra bits and get within 1/2 ULP of the exact answer. The faithful rounding is less demanding. It allows for 1 ULP of error. And most of the time, I have no doubt about this, it's more or less happy-go-lucky rounding. We have no idea of the real discrepancy in most of our functions. Okay, yet another important point, even if rounding is not linear because you shift after some cut value from one value to another one, so it's highly nonlinear, but this is completely deterministic. You can reason about it, even if it's quite difficult. We have spoken of this without precisely defining what is machine epsilon, which is in fact, in some sense, the quantum of precision of your type. So there are two definitions, rather formal one, but the mainstream definition is used in all the language constants that describe your types in Ada, C, C++, Fortran, Python, and Rust, and so on even MATLAB. So the machine epsilon is the distance between 1 and the next representable floating point number. You can see it also as 1 ULP after 1, or equivalently as the largest relative interval between two nearest numbers in finite precision, which is multiplying the first line by some power of 2. In other words, mathematically, it's the minimum of some set. All these definitions are equivalent. And the typical value you get are, for half precision, 9 10 to the minus 4, and for float, 1.2 to the minus 7, for double, 2.2 to the minus 16. So it helps you know what is the best result you can get. If you want to link to the formal definition, most of the time the formal definition leads to half this value. So it's only a conventional issue in most of the time. And so the significance of this machine epsilon is it gives us a rough measure of how close two floating point numbers can be before they merge into one representable value. It's the resolution of our computing instrument in some sense. As we have seen, every decimal is not a binary, so even the operation of conversion to binary relies on rounding. We have seen this for 0.2, and here for the value of an inch in millimeters, we see that no type as large as quadruple, if you want, gets it right. What is more surprising is the opposite conversion. When you want to display what you have just computed in the heart of your CPU, every binary is a decimal. But what you print out with std_cout, with print, with whatever I/O device you want, whatever you print out in decimal is not the exact corresponding decimal. It would require too many meaningless decimal digits. So I don't enter into these aspects, but conversion to decimal also relies on rounding. And so we want to avoid by any means the loops of passing numbers between functions or programs using their decimal representation, because we have a loop of rounding from decimal to binaries and rounding from this binary to decimal and so on. So avoid this. If you really have to play with decimal number, like in the case of financial computation, then okay, starting from C23, there should be decimal floating point. They are floating around in some sense for over 20 years, but libraries are tedious to use. It's not quite entered in the familiar language and compiler you can use, except when you program in SQL or COBOL, and for obvious reasons. So you can also change the scale of your representation. You can count hundreds, I mean cents, as integer if you need two exact places, or you can use in language that allows for it fixed point representation instead of floating point. Okay, so for something more mathematical, we have some value of pi in our language, or we can define some constant called pi, but how far is it from the mathematical pi that has an infinite number of decimals? So even in decimal, we couldn't have it. We expect that the sign of this pi will be 0, and the cos of this pi will be -1. And when we display the result in FP32, FP64, and in some sense in FP16, we don't quite get it. Sign, in particular, is wrong all the way. And when you take other special angles like pi over 6 or pi over 3, you also have some small discrepancies. So it means that the representation error for your constant is always perturbating your result. So if this discrepancy is a problem, you have to reconsider your coding and use after trigonometric function. Starting from C23, you have in your math library sin pi, cos pi, which are not the simple sine of pi times x. It's a dedicated numerical function that gives you sine pi of 1 is 0, and cos pi of 1 is -1. Okay, you can also use degrees trigonometric function, which is not the simple sine of x over pi times 180. All good Fortran compiler for years, plus the new standard Fortran 23 allows for it, so it will yet take some time to enter all the good mathematical library. Another aspect is with the humblest operation, the addition. It has a quite bad property called absorption. So we will address it with computing harmonic numbers. So the harmonic series, the sum of reciprocal of integers is diverging like the log of the n term of the sum. Here you can see the asymptotics of this series. In the table, I will limit my harmonic sum for half precision and give you also 2 examples in single precision FP32. So when we sum the reciprocal of integers starting with 1 and getting to smaller and smaller reciprocals, we get the column that I call the upsum. And I show you also the downsum when instead of summing from 1 to n, you sum from n to 1. And for the theoretical sum, I have been using this asymptotic development shown here. For small value of n, you don't see much discrepancy, but for 250, you already have some discrepancy between the upsum and the downsum. And the discrepancy gets bigger when you double n, and doubling again, you are saturating the value of the upsum. It's not yet sensitive anymore to whatever reciprocal you can add on top of this, during which your downsum is keeping rather close to the theoretical sum. Okay, with 1000 number, you already start to see some discrepancy, and this discrepancy goes larger and larger until for 8000, somewhere between 8,000 and 4,000, you are saturating your downsum. And the theoretical sum is diverging, so you know you will always expand on it. Before seeing similar discrepancies in FP32, you have to reach of the order of 3 million. So FP16 should not be taken lightly. But is there not some way so the program to get this here in modern Fortran is rather simple. Here you sum getting to the biggest number, and here you sum getting to from the top to the bottom. So is there some way to compute this sum more accurately? So this is called the compensated summation, the Kahn-Babushka, the William Kahn of the first pages. The Kahn-Babushka summation keeps track of some accumulator, as usual, plus a compensation that allows you to collect all the bits you are losing on the way. And the result of this humble algorithm, you see, you have 8 lines, allows you to go much farther before the two series start to have some discrepancy with the, okay, I have also computed the result in double precision to compare it to half precision, and it's not fair, I know, but you can go to 128,000 before noticing a very large discrepancy. And some other point is whether you do the Kahn summation from bottom down or from top down, you get the same result, which is very encouraging. So you see, we can keep a meaningful result by using this trick of Kahn summation, and I encourage you to do so. Here we have a large hierarchy of operation. We have started with arithmetics, plus, minus, multiply, divide, as well as the integer powers that are multiplication. We have the algebraic operation, the square root and the cube root and nth root, as well as fractional powers and roots of polynomial as well are algebraic. We then turn to elementary transcendental functions, which are exponential, log, sine, cos, all circular and trigonometric and hyperbolic trigonometry, on what we call special functions, higher transcendental functions, and their lesions. So the correct rounding is only guaranteed by the standard for all the arithmetic operation as well as the square root. What remains is not guaranteed, and particularly be wary of transcendental functions. They are costly, and their correct rounding is not guaranteed. So Hadrien was already warning you about forgetting your trigonometry. I double down on this warning. Know your trigonometry to avoid computing piles of transcendental functions. The rounding is nonlinear, and as such, it is mixing various scales of your phenomenon. And this mixing of various scales is what starts runoff, what we can see as a butterfly effect in this meteorology. So to get the correct rounding with so many bits, here double precision, so 16 decimal digit, you can see in the paper of Zimmerman that you may require 32 digits to only round correctly to 16 digits. So if you compute in high precision, for instance, a long double, and you round to double, then to float, or as will become more and more familiar in our generation, if you compute in double precision to round to float, then to half precision, it can also give worse final rounding than expected. It looks like a good idea, but it is not. Okay, these are mathematical considerations. What real physics needs double? So some people may consider that our float, single precision float, are well large enough for whatever consideration we want. But this is not the case. So you may know of the black body radiation, which is given by the Stefan-Boltzmann formula. And we'll compute in this simple Fortran program, but you can try it in whichever language you want with a single precision. If you compute the value of the Stefan-Boltzmann constant, so I give the exact value here so that you know what to expect. If you compute naively using the formula here and translating it in the computer language, you will get not a number. Okay, and if you instead compute it by rearranging the powers so that the large is divided by the large before being exponentiated, then you have something meaningful. But this is not the worst. The core of this seminar is what we call the catastrophic cancellation. So this first slide is by way of exception in base 10, not in binary. We'll imagine we have a half precision decimal floating point type with only 3 decimal digits. And for the value of A and B given here, the difference that this computer would give is 0.01. So we had 3 meaningful decimal digits, and then only the last decimal remains. So we have what we call the cancellation. We have reduced the relative accuracy. But this cancellation is a benign one. The floating point result is exact. What you get after the decimal rounding, we are not in binary on only this slide. The floating point result is exact. It's equal for the computer and for the mathematics. When in turn you try to compute the difference of squares, the exact result should be 6.67 10 to the minus 2, but the computed result in this particular computer, in this imaginary computer, is 0.1. So you have 50% of relative error on the result, or as much as 333 units in the last place. No digit of your displayed result is even correct. We call this a catastrophic cancellation. And so our first question is, when does this occur? How many digits are lost? Here, all digits are lost. So you have a lot of less catastrophic cases, but this is the most catastrophic. Okay, so on top of this, as you are computing squares, there is an overflow risk, but okay, not for today. Let's first factorize this. In turn, we'll get rid of the overflow risk. So a squared minus b squared is a plus b times a minus b. And when we use this factorized formula, our results get exact. So this is the right way to proceed in your computation. Try to get as much as possible. Most of the time, it's more accurate to get the factorized version. So every year, I get complaints that, oh, I tried your computation and it's not at all that catastrophic, but nobody, I believe, has a computer with a type of 3 decimal digit in Mantissa in base 10. So let me show you what it gives in binary. So the very new type of half precision FP16 has a mantissa of 10 binary digits. And if you try with the given number, the same computation, you go along the same way, and the cancellation is as catastrophic as in decimal. So I can also provide you with a FP32 number, which is easier, less frightening, but as catastrophic as this. So in this case, the factorized version gives us a result within 0.35 ULP. So it's the correct rounding. So we know that we cannot do better. if we don't use the factorized version, no digit is even correct. So this is a real issue. And as you understand, this was a catastrophic cancellation, but here I will show you the cursed cancellation, because higher degree polynomial can degrade high resolution even higher. If you consider the formula of Siegfried ramp with the given number here, if you evaluate in float, you get this value, why not? So to get a second opinion, you compute it in double, and then you lose 8 orders of magnitude. So you compute it with long double, and the sign is changing, and the magnitude is also decreasing by 4 orders. Then you go to quad, and you lose all your order of magnitudes. So from the start, we have changed sign, and we have lost 29th order of magnitude. It's enormous. Okay, FP16 are simply out of the way. They give you not a number from the start. So useless. And the exact result has in fact the negative sign, and it's even smaller than the quadruple precision. It can also be expressed as a quite simple fraction. But this exact result would have gotten an accurate representation in any precision. Even in FP16, you can represent it by the fraction given here of that leads to minus 0.82. So this result can be represented accurately in any precision, but it cannot be computed in any precision. So here we have the fundamental problem that I wanted to address today. In turn, it will be how to control the rounding errors. Because for this kind of polynomials, you are not guaranteed any kind of factorization, even from the theory side. Practically, it's impossible to get it. So when we address one variable polynomial evaluation, you should always stick to the Horner-Ruffini evaluation to avoid the computational cost of all the exponentiation as well as the accuracy loss it represents. So instead of summing this, you would sum this way. So this is the way to go. It provides you with a gain in speed by saving operations, also a gain in accuracy, partly for the same reason, and it's a guarantee of stability of the result and safety against intermediate overshoot for multiply and accumulate machine instruction. And if you also combine it with the summation techniques such as the algorithm of Kahan, you can go even better. Okay, so I have already exceeded my allotted time, so I leave it to you to consider things such as variance on all statistics, because there are difference of square of sum and sum of square. I don't go into the typical computation, and I encourage you to read about comparing floats because these are subtraction, in particular comparing floats to 0 on what it impacts for unit test. So it's way time that I leave the mic to Hadrien.
I wanted to spend a bit of time showing you some of the weird stuff that can happen when subnormal numbers that Vincent briefly mentioned at the beginning of his presentation intervene into a computation. First, a bit of context. In the microarchitecture course that I gave last week, you obviously started to get a taste of how complex modern computing hardware can get. And one thing I mentioned at the time is that in some cases, the performance of hardware operations can actually depend on the input that you send into the operations. The most obvious case that everyone can think about is memory access performance, which can change because you have CPU caches. If data is in cache, the memory access will be faster. But this is a more general thing that anytime you see a single number metric describing, this CPU instruction has this performance, often that metric has been measured in a typical case where the instruction is used, or if it has been measured by a hardware manufacturer, it can even have been measured in an over-optimistic best case. And today I want to show you a more complex example of that. So recall that the floating point numbers we use today are encoded using a variation of scientific notation in base 2. And in the normal case, the way this works is you have a sign bit, and this tells you whether the number is positive or negative. You have a number of fraction bits, and you put them after 1 point something, and this tells you the mantissa of your number. And then you have an exponent which you bias to get the power of 2 that you're dealing with. Notice that there is a trick that has been played by the IJCLab 754 designers here, which is that they realize that because if you do scientific notation in binary, the leading digit is always going to be 1. You do not need to encode that 1. And this means that you can save 1 bit of storage inside of your registers and encode more numbers in equal space. And considering the time at which floating point numbers were designed, this was seen as a great quality. There is just one problem. How do we encode the number 0, which is very useful using this scheme? We cannot. So what the IEEE 754 designers did was to say, oh, that's okay. We are just going to introduce a special case when the exponent is minimal. Instead of treating the leading bit of the mantissa as 1, we'll treat it as 0. And hopefully the hardware people will figure out a way to make that efficient. Many years later, I keep getting hit by an annoying phenomenon where regularly I end up writing code that runs much slower on Intel CPUs than on AMD CPUs. And usually I don't notice right away. I notice when I'm late for some work and I bring some work at home and I run the code that I'm working on my AMD CPUs at home, and I notice, whoa, that's so much faster. What's going on here? So I take my trusty profiler, I do some profiling, I find hot functions, then I drill down into the assembly of those hot functions, and I see that most of the CPU time is spent on processing floating point arithmetic instructions. That's a good thing. It takes me quite a bit of work to get there. Obviously, however, there's something going on with those floating point instructions that's different between Intel and AMD because, the CPUs from both manufacturers are different, but in a single generation, you don't explain more than a factor of 10 in performance just with that CPU is so much faster. There's something else going on. So you can search the internet for information about this problem, and there is some stuff that you will easily find. The easy stuff is that the floating point arithmetic units of CPUs struggle with subnormal inputs very often, which is a problem because any computation that features some component of spatial diffusion or exponential decay will eventually produce subnormal results. Because if you take a number and you take a certain quantity of something and you spread it over space in an infinitely large space, at some point your local density of matter will be tiny. And if you have something that decays over time in an exponential way, you will end up with tiny numbers as well. And if you combine the two, then due to round-off error, you will keep having subnormal numbers everywhere in your simulated domain. Another stuff you will find is that that's actually not big of an issue, people think, because you can just disable the CPU's ability to process subnormal numbers with a global flag that affects all computations carried out by the program. And then there is no penalty anymore for the processing of subnormal numbers. They are just treated as if they were 0, which is already a special case to be fast. That's the easy stuff. Now, if you spend a bit more time searching like I do, then you will find other things. Like this seems to be a much bigger problem for Intel CPUs for some reason. Some rumors on the internet say that actually Intel took a very inefficient approach to implementing subnormal mathematics. They do it by trapping into a microcode emulation. You will also find that it's not as easy as just manipulating global CPU state, because that is undefined behavior in many languages, which means that as soon as you do this, you have no guarantee anymore that your compiler will produce sensible output out of your program. And if you search extra hard in applied mathematical circles, you will also find that disabling the processing of subnormal numbers will break many important mathematical algorithms in fields like iterative algorithms, minimization algorithms, and so on. Maybe the situation is not that simple. Another thing you will find is it's very hard to get good quantitative data on this phenomenon. The data you find only covers very old CPU models. It's not clear which operations are affected by subnormal numbers and how, to which extent each individual operation is affected. It's not clear what kind of input data people use in their benchmark and why they use this sort of data. And when people study remediation strategies, they only study the global flag strategy, which, as we've seen, is a bit problematic. This is why I started writing a better macro benchmark of the behavior of CPUs in the face of subnormal mathematics. It's still work in progress, but it's getting there. And today's talk is going to present some work in progress research results, so please respect that. So what am I doing here? I am taking each common floating point operation that is implemented in hardware, and if necessary, I combine it with other operations that are also implemented in hardware in order to get a binary pseudo operation that, given an initial accumulator, which is a normal number, and an input, which may or may not be a subnormal number, produces an updated accumulator, which is a normal number. And this means that over accumulation iterations, we can study what's the effect of performing a certain number of operations where a certain share of operations encounter one subnormal input and the others do not. It's not enough, however, for reasons that I do not have to go into. We also need to use a special input generation strategy. Obviously, we need to enforce a controlled share of subnormal inputs in order to study how the behavior of hardware varies when we change the share of subnormal numbers in the input data set. And we also need to keep both accumulators and normal inputs in a relatively narrow magnitude range. And the reason why that is we do not know what hardware is doing. And for all we know, some hardware may have performance that depends not on subnormal inputs, but on subnormal results. And as soon as the accumulators start getting in a very wide magnitude range, it's very hard to assess what is the share of subnormal results in our computations. Then once we have the basic design, we can do lots and lots of combinatorics, as usual when studying hardware. So we need to take our workload, we run it many times for many data types, because we have single precision, double precision, all kinds of vectorization, which may be implemented differently for all we know. We have many floating point operations that are supported in hardware. We also need to study the effect of instruction level parallelism, because the penalty that we pay for subnormal mathematics may be more of an instruction latency penalty or more of an instruction throughput penalty. And the only way we can differentiate between these two is to study both computations with a single dependency chain, which are latency bound, or computation with multiple dependency chains, which hopefully should become at some point throughput bound. We also want to study how the effect varies when data comes from certain locations. Not that I expect this to directly affect the performance of arithmetic. However, it is necessary to get a fair assessment, because if I tell you that, subnormal math is super slow when input comes from register, and you tell me, yeah, but all my inputs come from RAM, I agree with you. Maybe you have more memory access performance problems, and thus subnormal performance is not as much as a priority for you. And finally, obviously, we want to study this for various shares of subnormal numbers in the inputs and repeat the benchmark workload several times with a varying number of iterations per time run in order to detect instability in the running time and nonlinearity as the number of iterations increase. Given all this, for a given benchmark configuration, we get a set of timing samples, which give us the average duration of one operation. You can see these samples plotted on the horizontal axis of this graph as blue semi-transparent lines. And then we can use those samples to estimate the probability density of having a certain benchmark execution time. And here I'm hiding a huge amount of complicated mathematics under the rug, because the probability laws that are followed by benchmark execution times are not at all, they do not have common mathematical properties. They are not Gaussian. They are not necessarily unimodal. So all the stuff that you are used to do in statistics is broken, and you need to use weird statistics like kernel density estimation with a variable width. Again, I will not go into details. If someone is really interested, I can go into detail later in the questions. Sufficient to say that once we have this, we can then plot this number. We can take this plot, and now we turn it into a color-coded line, and we plot one column per share of subnormal number, and we study the behavior of the average duration, and more precisely the probability of getting a typical iteration duration from 1-1. Now, what does that look like? So let's first take my main CPU from work, Comet Lake CPU from Intel. We can do additions, and we see that we get mostly constant timing. It's not affected by subnormal inputs. We can study maximum, also is not affected. Then we can study square roots. Here we have a problem because the square root of a subnormal number is a normal number, and we need some notion of accumulation that does not exist for square roots because it's a unary operation. So we need to play a trick by combining square roots with a maximum. And here you see that we start to see a big penalty where if you have lots of subnormal, you have like an operation that starts taking in around 40 nanoseconds, whereas it was taking 1 nanosecond before. So that's a 40 times penalty. That's not good. You can also do it with multiplication. You get the same thing. Division, you get the same thing, whether the input is the numerator or the denominator. You can do it with FMA with the subnormal input in various positions. You get the same thing. And if you have two different subnormal inputs, then the probability of getting one subnormal input approximately the so you know you get one chance of having a subnormal input in each of these inputs, and so you get this nonlinear evolution law, which looks very pretty. Overall, what we can conclude here is that addition, subtraction, minimum, maximum are not affected, but on Intel, any other operation pays a huge penalty for subnormal numbers. You pay it if any input of an operation is a non-zero subnormal number. And what I don't have the time to show you, but I have done my homework, is that you get similar behavior across all data types, and the penalty gets worse as the amount of instruction level parallelism increase, because essentially your operations that used to be throughput bound and thus faster become latency bound, because the latency of processing one single subnormal number is so enormous. What does it look like on my CPU at home now from AMD around the same time? You see that the timings are a bit less stable, but overall addition is still not affected. Maximum either. But for square root, we start seeing different things. So here you see that to compute one square root, it took 1.1 nanosecond before. And here there is this interesting behavior where the performance does degrade about by a factor of 2, less than a factor of 2. It's much less severe than on Intel CPUs. But there is this interesting phenomenon where the degradation happens quite quickly as the share of subnormal numbers increases, and then it stays constant. So I'm pretty sure that the reason why this happens is a trade secret, so I can only give you speculation. But my assumption is that what's going on is the AMD CPUs have actually two operating modes, one in which they process normal numbers very fast, and one in which they can process both normal and subnormal numbers, but a bit slower. And my understanding is that anytime the CPU encounters a subnormal number, it switches to that slow mode for a while. At some point, when you have enough subnormal input, then the average spacing between subnormal input becomes less than the cooldown time after which the CPU switches back to the fast normal processing mode, and thus you get a fast increase and then a slow. Now, where it gets interesting, however, is what happens when you study multiplication. And here what you can see is that actually our timing probability law is not unimodal anymore, it's bimodal. And if you were wondering why I'm doing all this trouble with kernel density estimators, that's why. Benchmark timings are too complicated as probability laws to be represented by single number statistics without formal precaution to check that this is actually a correct thing to do. So here it's not clear to me yet why that might be happening. It looks like the CPU switches between two operating modes across different runs, and I don't know why. What I can tell you is that there is one execution mode that looks like the square root mode, where you have some early penalty and then it stays mostly constant. And there is one mode that's a bit weirder, but gets cheaper in the end. And you can see that overall, again, the penalty is not that large as far as orders of magnitude is concerned. We are less than a factor of 2 slower. Division behaves like square roots. Again, whether you put the input at the numerator or denominator, it does affect things a bit, but not that much. It does increase latency, however. But what's even more interesting, I believe, is that fuse multiply add is not affected at all. And this violates many of my assumptions about how hardware is supposed to work. I have always thought personally that in modern CPUs, multiply was implemented as a fuse multiply add with a 0 addend. And this is proof that this is not the case, right? The CPU is here obviously using a completely different implementation for fuse multiply add than for multiply, which allows it to pay no penalty for subnormal number when doing FMAs, even if it does pay penalty when doing multiplies. And I find that very interesting. So I unfortunately was a bit short on time, so I did not get the time to write the conclusion slide of this presentation, but overall, I hope you found this interesting. Again, this is work in progress research. There are many questions, more questions than answers. But my hope is that by setting up such a robust and exhaustive benchmarking infrastructure, I can get better insight into the behavior of CPUs in the face of subnormal number, and I can more easily study alternative strategies to the global flag strategy, which people are usually satisfied with, but it has many problems, and in my opinion, it should therefore not always be the go-to solution. Thanks for your attention.
Thank you, Vincent and Hadrien. So we have some questions for Vincent first. So are the results still accurate today with modern computers? From Idris.
Okay, so yes, the papers of RAMP on, in fact, these results are not in exactly this paper, but in one of his book. So this paper, you can reproduce them nowadays on modern computers. Okay, the accuracy issue does not depend on the specificities of the hardware implementation. They were true before IEEE, and they are still true nowadays. We don't get different things in this respect. So this was compiled 3 years ago and reproduced 2 and 1 year ago as well. So what can I say? It's yes. The modern computers are no more accurate than the earliest one as far as floating point computation is under study. Does it answer the question?
Okay, yes. Okay, maybe a question for Hadrien from Julien. When benchmarking on Intel and AMD, did you compare the result values on both architectures?
I clarify first that this was about the output of the computations, and normally the IEEE 754 standard guarantees that all the operations I discussed, so addition, subtraction, multiplication, FNA, and square roots, should produce the same result, bitwise result on each hardware. However, I did not check for this explicitly.
Okay, so I have another question related to that, not on the results themselves, but how you handle the initialization of your denormals. Because when you present your plot with the Ryzen AMD with two branches of the of the result, I assume it's just an idea, but I assume maybe it could be a matter of sequence. If you have a lot of denormal following each other, not standard number following each other, maybe the CPU can switch mode. Is a kind of, I don't know, branching predicator for subnormals, and then maybe they can have some performance that way. It could be explained the two modes that you observe.
I'm assuming there might be a data-dependent phenomenon at work, but that's a much more complicated analysis, and I did not get the time to do it yet.
Okay. Because I'm wondering, maybe if you say, okay, I want, I don't know, 50% of denormals in my table, but I want them to be contiguous for the first half and then the other half without to see if it can change the result drastically or not. It'd be a nice thing to do.
Yeah, you mean if I just bias the random number generator by grouping all the subnormals and then all the normals? Yeah, that could be one easy test. I agree.
Yeah. So in that way, you can say, okay, if I master the distribution of my denormal I have in my vector, and then I can say, okay, if I have 50%, but only contiguous, on in 4, 3, 10 times 10 sequences, you can see what are the performance, and you can plot it with the average size of the.
There are also other analyses that I have not done yet that I would like to do as well. Like, I wonder if this depends, for example, on the number of benchmark iterations. Right now, I have just, taken benchmarks running at various numbers of iterations and compared the average running times.
Yeah.
But if there is some kind of mode switch going on, it could depend on how long you are running the benchmark for. So that also, studying this behavior could be interesting with stuff like piecewise linear regression. There are many, again. This looks interesting, but I did not have the time to go at this level of analysis before this talk.
Yeah, for sure, it's a big work.
There is one extra question from David. Do we have a feeling about what is the subnormal share in typical scientific computing? Oh, well, that's a great thing to study next in your computations. You can study it for a particular computation and for a particular input data set. But the dangerous thing is that this is dataset dependent, right? For example, in audio processing, people who process audio signals with computers, there is a saying that silence is deadly, because when you have a real-time audio effect which processes a sliding window of input data, and for a while the input data is silence, which in hardware means noise in audio, you suddenly get lots of tiny input values, and then you get lots of subnormals, and your program slows down to a halt, which means that in audio processing, what used to be a smooth running filter becomes a filter that eats more than its allocated CPU budget and starts skipping audio and producing horrible artifacts in the sound that you record or listen to. This, because this is a data-dependent question, it's well possible that we can have programs that are particularly vulnerable to subnormal inputs, but have never been tested with them. And so we will only know when someone runs them in some particular configuration that is more harder for hardware to handle.
Yeah, and also with some numbers, as you mentioned, you can have way different performances by respect to the hardware you are using. If you use hardware from 5 years or something like that, you can have much more problem with this.
So in the chat, Kevin is asking, Hadrien, did you run the same sort of benchmark on a supercomputer? And if so, does the hardware perform differently from that in a simple laptop or desktop computer? I did not have the time to run it on more hardware platforms. Actually, I run the benchmarks on 2 more computers using different Intel and AMD architectures, but that there was already a bit too much content in this for the duration that I had in this presentation, so I did not try to cover it. What I can tell you is supercomputing hardware mostly has the same qualitative architectural decision as a desktop hardware. It's just the quantitative decisions, the tuning parameters that change. Like you will have more or less cache, more or less memory bandwidth, but I do not expect qualitatively different behavior. And in particular, I do not expect floating points arithmetic units to be different. And so I expect performance characteristics to be the same.
What about GPUs, qualitative differences?
I did not have the time to do the test on GPUs. Once I find it, I will tell you.
Yeah, we have a lot of things to say about GPUs, but maybe for today it's a bit too much.
But another hardware to be tested as well that I would be interested in is ARM CPUs.
Yeah.
I suspect they may do some things differently here as well.
Okay, thanks from Laurent. Okay, people start to thank you for the presentation. So maybe it's time to stop. So thank you for joining us. Thank you, Vincent, Hadrien, for the nice presentation. Of course, we will have much more in the school, so to play with. But we have to keep a bit of content for the school also. Okay, a lot of thank you in the chat. Yes, that's definitely the time to stop. So thank you everyone for attending this webinar. Next week it will be Sébastien about memory management, allocation, the impact of your memory allocation on your applications and how to profile everything. So don't miss it. It will be also quite interesting. And have a good day and see you next week.